Okay, so good evening again. This is Dr. Jensen for Nomenclature. So nomenclature deals with chemical naming. Now, in general chemistry, we have a variety of different kinds of elements that we've talked about: metals, metalloids, nonmetals. And so when these things come together, they're going to form a variety of compounds, right? We have ionic compounds, which are a formation of metals and nonmetals. The reason why they form in that way is because of their opposite charges, because of their difference in charges. Like two magnets, they stick together. Okay, we have they're made up of nonmetals. So here, these compounds are not they're not charges, so they end up being more of a sharing. And then we have metals, which bond through various metallic bonds where their electrons become kind of a sea of electrons, or they have a sea of electrons, and so it's not really like it's not quite the same as a covalent or ionic bond as metals bonding. So where we're going to focus is on the ionic and the covalent nomenclature, right? When we get to the next chapter and we start looking at molecules, like putting them together or what do they look like, we're going to focus more on the covalent compounds, because ionic compounds are not as interesting per se when we look at structures, at least not from one particular structure aspect, right? Which is our Vesper structure. So most of our bonding is driven by what's called electronegativity. Okay, it is a chemical or atomic property that deals with an atom's pull on electrons. Okay, and so down here at the bottom you have the periodic table. Okay, and so electronegativity increases as you go this way across the periodic table and up. Okay, so the stronger, more electronegative atoms have a stronger pull on electrons. Okay, and so this is how we get the difference in charges. So we talked about in one of the chapters, in chapter 2, that the properties of metals were that they lose electrons. Okay, here's all of our metals. Okay, here's all of our metals. All these ones in blue are all metals. And one of their physical properties are they lose electrons. And they lose electrons because they have a relatively low electronegativity. They don't have a strong pull on those electrons. They don't have they're not strongly holding on to their electrons, and so they're easy to be lost. Whereas our nonmetals, okay, we talked about one of their common physical properties are that they gain electrons. They gain electrons because their electronegativity is so high. Okay, they want to have electrons, and so they will take them from other things. And in this case, if you're a strong electronegativity and there is a metal around, they take from the metals. The metals give up their electrons. So now we have a positive in the metal who has lost electrons and a negative in the nonmetal that has gained electrons, and they stick together like a magnet. The positive, the opposite charges are attracted to one another, and so they hold together like a magnet. Okay, so this difference in electronegativity is one of our main drivers for things like ionic bonding. Okay, so they bond because one atom has pulled electrons off the other. That's where the positive charges came from. Sodium is not positive by itself. It's positive because it lost its electron to some nonmetal. Okay, there's things like when we have charge distributions across elements, that we're not just going to end up with a solution where there are just positive charges. You're going to have solutions where there are positive and negative. They have to be balanced as far as their charges go. Okay. And our covalent bonds, okay, our covalent bonds, both nonmetals in this case, are relatively strong in their electronegativity. So one of them is not just going to be able to pull electrons off the other. So in order to have a bond, they end up sharing electrons. Okay. Now, this doesn't mean that it is an even sharing. Okay. Some nonmetals are stronger than others. And so as a result, we end up with uneven sharing of electrons. We end up with polar molecules. And so we'll get into some of that stuff later. So these are the common charges again. So this was in a previous slide. So this may look just slightly different than one of the previous slides. So since we're talking about nomenclature, these things are important for putting molecules together, okay? The group 1 cations, the alkali metals, are all +1. The alkali earth metals are all +2. They always have these charges. When they form an ion, they always form ions with these particular charges. Okay. The nomenclature PowerPoint should be under chapter 2. Right. I will, if it's not, I will put it there. We can take a pause and I can load it if it's not on there. So we can hang on one second. Okay, so our common charges are things that are going to be helpful for you when you're both building molecules and naming molecules. This also comes up again later in other segments. Okay, so knowing these kinds of things now, like I said, this comes up again when we deal with oxidation and reduction. So that'll be a chapter we'll talk about later where we talk about the loss and gain of electrons. So when atoms lose and gain electrons, we have to know what are their common charges. And so having these things memorized will help with some of that. And so this one you'll see things like zinc is +2, aluminum is +3. These are common charges. They're not all, oxygen's a steady one that you can go by for the most part. All right, so our simplest compound that we have to try and name are binary ionic compounds, okay? Where we have a metal and a non-metal. So this is how the names get done, okay? The metal keeps its name. So this is where knowing lots of metal names can be beneficial, right? Again, first semester general chemistry usually looks for about the first 20 elements. Then there's probably an additional 10 in there that are helpful to know. Things like iron, okay? So iron is not in the first, iron and zinc are not in the first 20 elements, okay? Bromine is not in the first 20 elements, okay? So, but there's a variety of these other ones that you should also know as well. And I'll give you a list of the other 10 on top of the first 20. Okay, so the metal keeps its name. The anion has a slight shift in its name to have an IDE ending. Okay, so instead of chlorine, it becomes chloride. Instead of bromine, it is bromide. Okay, so some examples here. So these are binary elements or binary ionic compounds in that there are 2 elements. So there's calcium and chlorine. Right? So it's not the fact that there's, it's not, this is not what they mean by binary in that there's 1 and 1 or 1 and 1. It can be 3 of them, right? So that's still a binary because there's sodium and nitrogen. Binary meaning there's only 2 different elements there. Okay, so calcium keeps its name. Chlorine becomes chloride. RB is not in your first 20. Rubidium, okay, so again, knowing lots of elements, you can get, so you can see right here, there, for the nomenclature quiz that you'll have, every problem is worth 1 point, but there's half of name here and half a name here. So if you know the element, if you know the metal, you can get a half a point for just putting the metal down, okay? Even if you don't know the second part, okay? So it's a production, so you accumulate points, or at least half points, enough half points that you get extra credit, okay? Rb is rubidium, and sulfur becomes sulfide, okay? Sodium and fluorine becomes fluoride. Magnesium and oxygen becomes oxide. Sodium and nitrogen becomes nitride. Okay? So the first element keeps its name. Second element has an IDE ending. Okay? Now, if we're going to put these together, okay, this is where those common charges comes into play. Okay? If I want to put together the compound aluminum chloride, okay, we need to know that aluminum is a +3. Okay? And we need to know that a chloride is -1. Okay? Now, when they form a molecule, the charges have to balance. Okay? I want to balance my positives with my negatives. Okay? So if I only have one chlorine, okay, that doesn't make a balanced molecule. That doesn't make a charge neutral molecule. Okay? So that's why I need 3 chlorines. Okay? I need 3 chlorines or 3 chlorides because I need to balance their charge against the +3 for the aluminum. Okay? That is how and why the molecules form the way they do. Okay? Is to balance those charges. Okay? So having these things memorized is what's going to be important if we're going to put molecules together. Okay? We have aluminum and oxygen. Okay? We need to know what are their charges if we're going to put them together. Okay? Aluminum is a +3. Oxygen is -2. So obviously a +3 and a -2 don't just balance each other. Right? So we have to apply a set of common denominators. Okay? What is the common denominator between 3 and 2? Okay? The common denominator is a 6. Right? So I have to multiply the aluminum by 2 in order to make a total of +6. I have to multiply the oxygen by 3 in order to get a total of -6. Right? For sodium, that we should know is +1, bromine is -1, they just easily go together. Okay? Barium is an alkali earth metal. So its common charge is +2, just like magnesium. Okay? All right? And calcium and oxygen are both positive and -2, respectively. Right? So we need to know this information as we put the molecule together. Right? And so the molecule forms as a function of those balanced charges. Okay. Now, there is a process called the drop and drag, which can be helpful in some situations, okay? Where the charge of the barium and the charge of the fluorine are going to swap positions, okay? And that becomes the subscript for the other molecule. Okay? If I take the 3 up here for the aluminum and bring it down, and the 2 for the oxygen and bring it down, aluminum is a 2, Al2, O3, right? For something like some of these other ones, it doesn't always work. Okay, so the drop and drag works most of the time. Okay, so we'll look at the instance where like calcium oxide, it doesn't work, right? I don't take the 2 and bring it down over here and the 2 and bring it down over here. Okay, so you don't end up with Ca2O2, right? Because the real fundamental issue of what's causing the bonding is the common charges. Okay, is the balancing of those common charges. Okay, so just like on the nomenclature quiz, we want to be able to, if I give you a compound, you want to be able to name it. Okay, so we have potassium chloride, magnesium bromide, and aluminum sulfide. Okay, so here's what I was saying. The drop and drag doesn't work just like the calcium oxide. It doesn't work for the magnesium oxide because magnesium is +2 and oxygen is -2. Okay, so it is not Mg2O2. So it more works where the charges are different. Okay, it works better where the charges are different. Okay, so the drop and drag is a tool, but like any tool, we have to know when to use it. Okay, if I have a hammer in my tool bag, okay, I don't go around using it if I need to put, you know, if I'm screwing stuff into a, you know, I'm doing electrical work. Okay, if I'm doing electrical work, you don't use hammers, right? At least for the most part, it's my experience. Right? So there are tools, but we have to know when to use them. Okay, so they don't always work in all situations. Okay, now there are a set of ions called polyatomic ions. All right, so polyatomic ions are, by their name, poly, meaning many, atomic, atoms, ions. So they are an ion like chloride, but they are made up of multiple atoms, okay? And so they may be a charged species as a whole, okay? So for these, when we have polyatomic ions, we don't change their name, okay? The name of the metal keeps its name. The name of the polyatomic ion keeps its name. Right? Now this obviously presents an issue where the polyatomic ion keeps its name, but you need to know what the name is. Okay? So for example, sodium hydroxide here, so OH is the polyatomic ion hydroxide. So you need to know that OH is hydroxide. Otherwise, how would you name that, right? CN is the polyatomic ion cyanide. So barium cyanide is the name. But if you don't know that CN is cyanide, how would you name that, right? And so what I end up getting is for people who don't know the polyatomic ions, I get barium carbon nitride, okay? Sodium oxygen hydride, okay? Or sodium, you know, sodium oxygen hydride or sodium oxide hydride kind of thing, right? So they just name all the elements and that's not how it works, okay? This is a unit, okay? Cyanide is one unit. It is two atoms that travel together that just happen to have their own charge, okay? So for the nomenclature quiz that I give, these are the common polyatomic ions that I would expect you to have memorized. Okay, you would need to know these polyatomic ions.
I have a question.
Yes.
Before on the previous slide, it said that polyatomic ions, the charge, that it doesn't change. So does that mean like covalent ions and the other ones that the charges change on them?
For covalent molecules, you're talking?
No, just like anything but polyatomic ions.
Well, okay. So ion charges are not set for a lot of atoms. Okay, for the group 1 and group 2 atoms. Okay, so let's go back to that chart here. Right. So the alkali metals and the alkali earth metals over here, they're always going to be +1 and +2.
Yes.
Okay? Always. Okay, you're not going to find a sodium that's anything but that. Okay, zinc is only +2, aluminum is only +3. All right, so the difference will be here in a minute when we talk about what is the difference between a charge and an oxidation state. Okay, so in a second here, I'm going to start talking about oxidation states, which are like a charge, but it's an electron counting. Okay, so
Yeah, same number.
When like chlorine is not always going to be -1. Right? It's -1 when it's by itself, right? But if you put chlorine and oxygen together, right, one of them has to be positive, right? Somebody's got to be positive, somebody's got to be negative, right? So, it's role-playing night in the non-metals, household. And so somebody's got to dress up and be one role and somebody's got to be the other role, right? So, in this case, a lot of times oxygen tends to be the negative, and then that makes whatever it's paired with have to play the role of the positive. Okay, so we'll see in oxidation states that these values may slightly shift.
So the one from the chlorine, does that transfer to the oxygen? Right.
Well, it's not when the chlorine and oxygen bond, it's not an ion. It's not a charge. They're sharing, but we're keeping track of the unequal sharing. Okay. It's the oxygen and chlorine are sharing electrons, but oxygen is unevenly sharing, and so we keep track of that, and it looks like a charge when we write it, but it's not really a charge, right? So it's a sharing of electrons. It's just we still have to keep track of what's happening even as they're sharing. Okay.
Yes, thank you.
So like I said, we'll come back to some of that again here shortly. So the polyatomic ions, their charges here, okay, don't change. Okay, so you need to know what is the charge on a hydroxide. So hydroxide is OH negative. Okay, you need to know the name, the formula, and the charge. Okay, acetate is C2H3O2 negative. Okay, so it is an organic molecule with a negative charge. Okay, so it is an ion. Right? So it is one big bulk of stuff that travels around with a negative charge. Okay, carbonate, CO3 -2. Okay, bicarbonate or hydrogen carbonate is -1. Nitrate, NO3 negative. Nitrite is NO2 negative. Cyanide, CN minus. Dichromate, here we have one of our only positives, ammonium. Okay, here we have a whole bunch of chlorine molecules. Hypochlorite, chlorite, chlorate, perchlorate, sulfate, sulfite, permanganate, and phosphate. So you basically just would have to have these memorized. Okay. Now, when they get into molecules, they just, you need to know what the formula is. So if we say potassium carbonate, if you're going to put this molecule together, you need to know what is the charge on a carbonate so that you can make the right molecule, so that you can put it together properly, right? Magnesium acetate. Okay, here you'll see the parentheses again. Okay, just like in the molecular weight problem that we may have done earlier, and that when we're looking at the acetate is one thing. The one acetate has a -1. So I need two of them. So there's one acetate here and one acetate here. But if I just simply put a 2 on there, then it looks like my formula is CH3CO22. Okay, I don't have 22 oxygens, I have 2 acetates. So it's 2 of everything in the parentheses. Okay. Potassium permanganate. Okay, again, the molecule, we need to know what its what the molecule is, what is its charge. Calcium sulfate. Okay, we've looked at the molecular weight for calcium sulfate. Lithium nitrate. Okay, the metal keeps its name. The polyatomic ion keeps its name. The charges don't change for the polyatomic ions. So the problem is that these sound very similar to one another. Nitrate and nitrite and nitride are 3 versions of nitrogen that are all very different. Sulfate, sulfite, and sulfide are 3 common ions of sulfur that are all very different. Ammonium is a polyatomic ion. Ammonia is not. Ammonia is a covalent molecule. Okay, so these are common mistakes when people are putting molecules together, naming, or writing formulas. So we have to be sure that we understand the difference of these. Okay. So there will be a video that I will do tomorrow on on putting some of these together, on doing some of the formula naming. Okay, how do we put names together? So I will work some practice problems in a video. All right. All right. Now, one thing you'll notice, okay, in all the examples so far, potassium, magnesium, potassium, calcium, lithium. Okay. Sodium, barium, magnesium, potassium, aluminum, or calcium. All of these were examples of basically using alkali metals or alkali earth metals, or something where the charge is pretty much set, where there isn't a definite, where there's no difference in the charge. Okay. However, okay, our transition metals, okay, that big block in the middle, okay, that big block of elements in the middle, okay, they have more than one charge for the most part. Okay. So how do we name iron oxide so that we can differentiate between iron oxide and another iron oxide? Right? If I'm talking about iron oxide and I want you to use the right one, okay, and you have 2 jars of iron oxide, how do you know which jar to use? So we need a further way to delineate the difference between the transition metal elements. Okay, and so we do that by adding the charge of one of each cation. Okay, the charge of the metal in Roman numerals in parentheses. Okay, so everything else in the thing, this formula stays the same. This is for the transition metal elements in the middle of the periodic table. Okay. The name of the metal keeps its name. Parentheses, Roman numeral, what is its charge? The non-metal has an IDE ending. Okay. So here's the examples here. Okay. We have iron oxide and another iron oxide. SN is tin, so we have tin oxide and another tin oxide. So how do we distinguish between these? The way we do it is by using the charge or oxidation state of the metal. Okay. Now, normally I would do a practice problem where I explain. So, this is kind of one of these situations where it's not really ideal for doing this virtually because I don't have my thing all set up here to do practice problems. So you'll have to look for the practice problem video where I'll come back and look at the specific examples of how do we name these specifically, okay? So we always know generally part of the molecule, okay? So for example here, this is copper, okay? Copper and OH is hydroxide, okay? So we know that the polyatomic ion hydroxide is -1, okay? You would have this part memorized, all right? So that means since there are 2 hydroxide, there's a total of -2. So my total negative charge is -2. So that means that the carbon, or I mean the copper, has to balance that out, okay? If the molecule being made had a charge, like it was a charged molecule, which again, there can be charged molecules, but if it was a charged molecule, its charge would be listed here, okay? Since there's nothing there, the overall charge of the molecule being made is 0. Okay, that means the copper and the hydroxide bond together and they have no overall charge. Their charge is 0. Okay, so that means my positives and my negatives balance each other out. Okay, 1 plus 1, or 1 and -1 makes 0, right? So in this case, I have -2. So what does the copper have to be in order for these two to go together? If the hydroxide is -2 total, okay, again, that's because there's 2 of them. So it's a total of -2. That means the copper has to balance that out as a +2. Okay. So I've been trying to wean over to talking about oxidation states rather than charges, okay? They are definitionally pretty much the same, okay? They are synonymous. Oxidation state is synonymous with the charge, okay? But oxidation state is a more of an umbrella term, okay? So every element has an oxidation state, but not every element has a charge, okay? So when we have something like an organic molecule that is covalently bonded, okay, the elements don't have charges, okay? They are sharing electrons in order to make a covalent molecule, okay? But we still want to keep track of the sharing, okay? Is the sharing unequal to one side or the other? So we still want to keep track of that by writing it down as an oxidation state, okay? So all of the metals that I already talked about, okay, so this same chart, so if you go back to this chart when you saw this before, it said the common charges. Now, I'm going to change that around, and I'm going to talk about these as oxidation states. So this is exactly the same slide, okay? The common oxidation state for the alkali metals is +1. The common oxidation state for the alkali earth metals is +2. Zinc's common oxidation state is +2. Aluminum's common oxidation state is +3. Oxygen is -2. The halogens tend to be -1. Okay, that is their common oxidation states. Okay, so from now on, when I talk about charges, I'm really going to say oxidation state. Okay, so I'm not going to really refer to things as charges from now on, okay? Because we're going to transition into covalent molecules that don't have a charge, okay? So here's a good example, okay? Methane, okay? CH4, okay? So the question is, what is the oxidation state on the carbon, okay? Carbon and hydrogen are covalently bonded. there is no charge here. There is no charge, okay? But the sharing of electrons is not entirely even, okay? Hydrogen is almost always going to be a +1, okay? For your purposes, the general chemistry, hydrogen is always going to be a +1 unless it is the element hydrogen, okay? Elements, okay? Elements in their natural state have a 0 oxidation state, okay? So elements in their natural state have a 0 oxidation state. So once hydrogen is bonded in a molecule, its only oxidation state is therefore +1, okay? So if I have 4 hydrogens, each of them is +1, that means I have a total positive value of +4, okay? Now, this looks a little weird here because now you're seeing the positive is on the right and the other one is a negative, whereas all the metals listed before were all positive on as the first one. The organic and covalent ones may not quite look exactly the same as the other ones. All right, so we have to go by a set of rules here in order to find the different parts. Okay, hydrogen is always going to be +1. Okay, that's one of our hard rules that we can use in order to find oxidation states for other things. Okay, so if all of the hydrogens are +4 as a total, that mean the carbon has to balance that out. Okay, carbon has to balance that out. So carbon's oxidation state is -4. Okay, it's not a charge. Okay, it hasn't fully lost electrons. It is an uneven sharing of electrons. It is an oxidation state. Okay, so let's look at this second molecule. Okay, carbon dioxide. Okay, oxygen has only 2 all right, let me take that back. I would say oxygen usually has only 2 oxidation states. Okay, there is a third, but we're not really going to worry about that right now. Right? It's either 0 when it's an element oxygen, okay, or most any other time it's going to be -2. Okay, so if there are 2 oxygens present, we have a total of -4. So this means the carbon then must balance the oxygens. Okay, the carbon therefore is now a +4. Two different molecules, 2 different oxidation states for carbon. In one molecule, it was a -4. In another molecule, it's +4. Okay. So oxidation states can change within the molecules, okay? But there is always something there that you're gonna know what part of it is. You're always gonna know half of the molecule, okay? There's not gonna be 2 unknowns here, okay? One of these molecules, you're gonna know, okay? Oxygen is one of our solid rock molecules or atoms that are going to be -2 that you can rely on for pretty much most of your general chemistry experience. Okay, when you're doing stuff in general chemistry, oxygen for the most part is going to be -2. Okay, you probably can't go wrong guessing that it's -2 because 99% of the time it is. Okay. So let's look back at that iron problem. Okay. Fe2O3. Okay. We don't know the iron. Okay. Iron is a transition element. It has multiple oxidation states. Oxygen does not. So each oxygen is -2, and there are 3 of them. So there's a total here of -6. All right. So that means the iron has to balance all that out. But there are 2 irons that are taking up that load. Okay. There's 2 irons balancing out all the positive. Okay. For the name, we want to know what is the charge on each iron. Okay. The whole positive 6 for the iron is distributed by the 2 irons. So each one is +3. So that's how we get the name iron 3 oxide. Okay.
Do they give the name like Fe iron 2 oxide? Do they give it like Fe2O3?
Well, for the Fe, no, for iron 2 oxide is a different molecule. So
no, like this right here, like Fe2O3.
Right. You would call it, you would say it's iron 3 oxide.
Okay, iron 3 oxide. Would they have that for us, or would we have to like make it?
Right. And so if you had to put the molecule together, you would have the name would be given as this. And so you would know that the iron is a +3 in this case.
Okay.
So this would have to be given if you get the name, right? So you either have the name or you have the formula. One of the two, you should have enough information to find the other.
Okay.
Okay. All right. So here's one of our tricky situations. Okay. From this previous slide here, right? What is the oxidation state on a chlorine usually? -1. Okay. Now let's go to that situation where we now are bonding chlorine with oxygen. Okay. ClO3 is one of your polyatomic ions. It is chlorate. Okay, so this is the chlorate ion. Right? So the question is, what is the oxidation state on the chlorine in the chlorate ion? Each oxygen is -2. Again, we're gonna go with that as our solid go-to. Okay, there are 3 of them. So there's a total of -6, but what's different here is the overall molecule has a charge. The overall molecule has a charge, which means that the oxidation states add up to that value. Okay, the oxidation states of the atoms add up to the charge of the molecule. Over here, the charge of the molecule was 0, right? Fe2O3, there's nothing written. There's no positive or negative written over here. So this is a neutral molecule. Its value is 0. So all of the oxidation states add up to 0 in this molecule. Over here, all of the oxidation states add up to -1 because there is a charge present. Okay, so we have chlorine and we have all of the oxygens at -6. So the question is then, what does chlorine have to be to make this expression true? It has to be +5, right? Chlorine must be +5 in order for +5 minus 6 to be -1. Okay. Chlorine cannot be -1 because -1 minus 6 is not -1. Right? The oxidation state for the chlorine changes. Okay? Because oxygen is more electronegative than chlorine is. So oxygen pulls the electrons towards it, leaving the chlorine feeling like it has less electrons. All right. So for transition elements, we may have to find the oxidation state based on what it's paired with. All right. Let's actually take a stop here for the night. Okay. And we'll regroup with this tomorrow.